I don't. Okay.
Yeah. Any questions?
No, I was just gonna say I don't see the screen, your screen yet. I just see your name, so I don't know if you've
okay.
made that known.
Let me see if you can see it. Can you see it now?
Nope.
My shares. Well, let me see. Oh no, not yet. Share screen.
Let's see if I do that. There's me.
Share. What about now?
Yeah, it's it says start share. I've got it. Good.
Oh, okay. Okay, very good. Okay. Now, today is the material we're going to cover today is more challenging. Okay, harder.
Yeah.
Harder than last week. Because after all this material we are using is for mathematical statistic, the applied mathematical statistic textbook. Okay, a little bit challenging. Okay, it requires calculus and integration, and so for that you will study a little bit harder. But smarter as well. If you run into any question, don't hesitate to ask. But I don't require memorizing or. Okay, that's good. Well, maybe you can you mute? Yeah, that'll be better. Okay, it sounds like your wife is cooking very hard for you.
Yeah, you're right. I should tell her to stop. I'll mute you.
Okay. Don't worry. Okay. Yeah, as long as you can hear my voice, that'll be great. Okay. All right. So okay. Let's get into it. The module. Okay. Today we will cover. We will cover special probability distributions and joint distributions. Okay. We will introduce some most commonly used distribution, like binomial probability distribution, Poisson distribution, normal distribution, T distribution. In the text, you also see gamma distribution and so forth. And that will lay a foundation for you to go far into the different real world application and different sectors in the industry. For example, in finance, if there's some area that you will explore or get a chance to touch, it use a lot of this kind of distributions. All right, and after that we'll cover joint probability distribution, and lastly limit theorem. They will become more abstract, but so try to follow me, and so you won't get lost. Okay, all right. Now, where's okay. Where's right here? Okay, and you can see I posted the material. E-textbook is already in there, which is convenient for you. Okay, let me see. Okay. Takes a little bit longer. All right. Okay, we will start with 3.2, 3.3, and 3.5. Hopefully, we can finish all these within an hour. Okay, make it bigger. Okay, when you open this slide, and sorry, I don't use PowerPoint, but I think this I'll go over this book as my lecture note. Okay, here this is the probability. We call it Bernoulli random variable. To understand binomial probability, we need to understand Bernoulli random variable first. Excuse me. Why? Because let's think of tossing coin n times. Each time is n, and this, if you toss a coin n time, that is a binomial experiment, and therefore the probability for the number of heads out of n times tossing coins will follow binomial probability distribution. The condition is each time you toss a coin, it's either head or tail with constant probability, 50-50, head or tail. Usually a coin is fair. So every time you toss a coin is either head or tail with equal chance for head or tail. But if you and then you do that n times, and that become a binomial distribution. But if you only do it one time, it become a Bernoulli experiment. Okay, so so we can say Bernoulli is a special case of binomial. Okay, and if you add n Bernoulli together, it becomes binomial. So that's their relationship. So, and each time you have a probability of success. P is a probability of success, okay? That means if you toss a coin, you got a head, and that's a P. That's a success, and that probability is P. Let's say usually 0.5. Can it be 0.4 and 0.6? Yes, depending on the situation. You can also turn the die tossing into a, we call it dichotomous outcome. It means two outcomes, success or failure, yes or no, true or false. And so in tossing a die, you have 6 numbers, but I can make it 2 outcomes by saying if I get 1 or 2, that's success. I win. If I get 3, 4, 5, 6, 3, 4, 5, 6, and then I lose. That's a tail. Okay, so the probability for head for success is 2/6. That's 1/3. And probability for head for tail for failure is 2/3. Okay, so that is that in that case you make the p different numbers from 0.5. Okay, so this is a Bernoulli, and based on that you have and probability. And so if okay, so in that case is if you have a success which is 1 and you plug in that formula, p to the 1 is p. 1 minus p to 1 minus 1 power will give you product equal to p. Okay, because any value has 0 power, it becomes 1. So p to the 1 is p times 1. is P. So P is expected value. And sorry, the P is the outcome when x equal to 1. And when x equal to 0, you plug 0 to the power p to the 0 is 1 times 1 minus p to the 1 minus 0 is 1 minus p. So the probability of x equal to 0 is 1 minus p. So that proves this. Okay, I just proved this right here. You plug x equal to 1 into this formula, you get p. You plug x equal to 0 into this formula, you get 1 minus p. So and so this is that. But then the mean is what? The expected value would be, okay, now you say x equal to 1 is probability is p, so 1 times p. And then x equal to 0 is probability is 1 minus p, so 0 times 1 minus p. So p plus p, 1 times p plus 0 times 1 minus p. But 0 times 1 minus p is 0. So 1 minus 1 times p is p. So that is the expected value right here. Okay, so on and so forth. I won't be able to prove all these with enough time. So you can use the formula and do it yourself according to the formula we saw it last week. Okay. Okay. Also, we won't get into too much detail to explain this formula. Okay. And instead, I will introduce a software called StatDisk, which make all these calculations very handy for you, okay, or Excel as well. So in the end, you will get this formula. You will get this formula to calculate the probability of binomial random variable. Okay, binomial random variable. Okay, so for example, let's say it is known that screws produced by a certain machine will be defective with probability 0.01 independently of each other. That's about one defective screw out of 100. Okay, and if you randomly pick 10 screws, that means n equal to 10, and it's like a unfair coin with probability of head is 0.01, very small. And if you toss it 10 times, how many heads are you expecting to have? Okay, so you plug in. So what is the probability? Oh, the question is, what is the probability that at least 2 screws will be defective? So this is how you turn your statement into formula. What is the probability? Okay, so probability with parentheses is what is the probability? At least 2 screws will be defective. At least 2. At least greater than or equal to 2 will be defective. X is number of defective items. So X greater than or equal to 2 will be equal to the sum of all probabilities. Okay, using these formulas twice by subtracting the probability of X equal to 1 and X equal to 0, you get the probability of X greater than equal to 2 or greater than 2 together. Okay, so but let me use a software which you can download and enjoy it, pretty handy. Okay, it's not powerful and not complete, but it's just handy. Okay, so let me show it to you. Let me send it. You can download it from statdisk.org. Okay, yeah, statdisk.org. And so if you go to that website, you'll see this. You can open an online edition. That if that's more handy for you, it's good. Otherwise, you can download it. It won't take up too much of the space, and then you can use it right here. Oh, okay. Click on analysis. Go to probability distribution and use binomial distribution. Okay, binomial distribution. And what is the number of attempts, trials? 10. What's the number of probability of success? Which is, we define the number of defective. If it's defective, is a success. So it's 0.01. So with that, you plug it in and evaluate. Guess what? You have everything. So if you go back to the where's my right here. Not this one. Sorry. Okay, you go back to this. Let's see, x greater than or equal to 2. The answer here is 0.004. So let's go back, 0.004. Look, x greater than 2, so you look at this row. Here it says x or greater. That means what x does it refer to? That refers to this row. When x is 2 or greater, is 0.00426662. You see, that's the same answer to here, 0.00462, and so forth. Okay, and so on and so forth. This will give you answer point probability or cumulative probability, okay, or cumulative probability from the other direction. Okay, and x equal to 0, x equal to 1. So you subtract these two numbers from 1, you will get the answer as well. But this is faster track. Okay, faster track. And the mean and standard deviation and variance are all given to you. Let's calculate. The mean is MP. N times P is 0.1. Variance is NPQ. N times P is 10 times 0.01. But Q is what? 1 minus P is 0.09. So NPQ is 0.099. And then you take the square root of variance, you get standard deviation, which is 0.3146. All these corresponds very well to the formula that you see here, right here, okay? PQ, and actually this is Bernoulli, sorry. The formula for the, is the mean. Oh, okay. Anyway, it's not hard. You just multiply, because I mentioned the combination of n Bernoulli is binomial. So the mean for binomial is n times p, and the mean variance is NPQ, because this is for Bernoulli, and so you times n, you get the formula for Bernoulli, for binomial, sorry. and then you take the square root of variance, you get the standard deviation for binomial. All right, where's the formula for binomial? Sorry, it's not shown here. Anyway, it doesn't matter. And you can use statistics to double check your answer with these. Okay, it will be the same. All right. So you using that will be a time saver. Oh, right here. Okay, right here. This is a binomial formula. Okay, just multiply n by the mean of Bernoulli will be it. Okay, and this is a proof showing you how you can get the formula. Okay, so if I don't quite emphasize the memorizing this formula. So you can, if you have time, you just get into it just yourself. Okay. All right. Then Poisson probability distribution. Poisson probability distribution is a very useful distribution introduced by the French mathematician Mr. Simeon Denis Poisson. Okay, wow, 1837. All right, so it's a useful probability distribution. You using as a counting random variable. Okay. All right, and this is a formula. Actually, this formula is derived from by using exponential function. Okay. Let me. Where is the? Okay, if you use an exponential function, let me. 1 second. Okay, if you use an exponential function, you will be able to derive it. Let me try to derive it for you here. Okay, how do you derive that formula? My mouth is not very good. Okay. All right. We know that exponential function is E is E lambda one to 1, yeah, 1 plus 0, 1, and 1 lambda plus E okay. This is exponential function. But let's multiply the both two sides by e to the lambda. Then it becomes what? E to the 0, which is 1. So we want to make the left-hand side 1, and so the right-hand side will be E negative lambda or negative lambda E negative lambda. Okay, so you can see the derivation here. You can easily find this is exponential function. Exponential function. Okay, if you type a Google search, you'll find this. Okay, then what? That means the proverb. Let's see, if we equate to this probability x equal to 0 corresponds to that one. Probability x equal to 1 corresponds to this one. 2 plus probability x equal to small x, capital X, small x, corresponds to this one. Okay, and to infinity. So that satisfies the condition for the probability x equal to I equal to 0 to infinity. So that satisfies the condition for probability distributions. So that's why it can be qualified as a probability distribution, and it's a useful one. Okay, let me save this. Poisson. Okay, let's come back. We have a lot to cover. Okay, so now you know how it come about, and this is the formula. Okay, again, you can use this. You can use this formula. You can derive this formula by. Let me see if we have it here. No, we don't have the proof how this come about, but you can prove it, okay? But just take it for now. So it's mean equal to lambda, variance equal to lambda. This is a special feature that Poisson has, okay? All right, and then we come to its calculation of the probability. Similar to binomial, you can either use a formula by plugging into the x several times in it to calculate the probability, or I would prefer to use statistics, and I will let you use statistics to calculate it. Okay. So let's do this question. What's lambda? Lambda equal to 0.5. 0.5. So what's the probability x equal to 0 and greater than or equal to 3? 0.665606 and 0.0143. So okay, let's use statistics. And click on analysis, probability distribution. You will see Poisson distribution 0.5. 0.5. Evaluate. Okay, voila. Okay, you got it. So here for x equal to 0, you get what? 0.606, right? The same answer. And greater than or equal to 2, right? 3. Greater than or equal to 3. Okay, so that 0.01439. 0.01439. You got that? Okay. So, but there's no magic in statistics because it used this formula. Okay, the same formula we went about here. This formula, and you can see its mean is lambda is 0.5, variance is 0.5. Variance is 0.5, mean is 0.5, and take the square root of 0.5, you get 0.7071. Okay, so in the same way you can calculate the rest of the questions without any problem. But here is a interesting characteristic that is that Poisson approximation. Yeah. Okay, Poisson approximation to binomial. When you have a large n and you have very small p, n p equal to lambda, which means it approaches, binomial approaches what? Approaches Poisson. This is the special feature as well. Okay. By the way, we know that all the probability distributions are in the same family. It's a big family, and you have so many family members. They are all cousins or nephews, or they are all relatives. They have similar DNA. Okay, you relax one of the conditions, one become the other easily. In this, you see this example already. And then if you have if you relax some other condition, then binomial become can be approximated by normal distribution later. You can see in the maybe in the textbook somewhere. Okay. Now let's come to continuous distributions. And for discrete probability distributions, we use summation. But for continuous probability distribution, we use integration. Okay, integration. And so, as we also covered that last week. Okay, actually, this integral sign here is equal to the what? Is equal to this integral sign here is equal to the this integral sign here is equal to this integral sign here is equal to limit n goes to infinity. It's like you know, this is suppose this is a curve. This is function f. So given a very small interval dx, your height, since it's a very small interval, it's equivalent to a square. At this point of x and x plus dx, okay, so the width is dx. Also, width times height is the area. And then so if you divide all the area under the curve into n rectangles, similar to that, n rectangles. I'm using microscopic to look at this. It's all very small. And then take the sum of it, you will be able to get the area under the smooth curve. But this is cumbersome to write this whole thing, so we use the integral sign instead. Okay, so that is the case with continuous random variable. All right, so now here, let's go on. Uniform, okay, another probability distribution is uniform. How do I? Uniform probability distribution, which is what? Uniform means uniform because its distribution is like a square or rectangle, like a rectangle. And so in order to calculate the probability, you draw a square. A and B, this is X. And this is f of X, which is the height, and the height is the probability. So this is that. And but the whole area under the curve is 1. And this width is B minus A. So its height is what? We know the width is B minus A. So the height must be B minus A over 1, so that the product of width times height gives equal to 1. B minus A times 1 over B minus A gives you 1 to satisfy the condition for being uniform distribution. Okay. And this is a cumulative probability. Okay, so in order to calculate the area under the curve, you use cumulative. You have to integrate. But since this curve is a constant, so it's just like it's not complicated. So it's just like calculating the area under a square. For example, I want to calculate area of X to the left. How do I calculate this area now that I know the height? So all I need to do is to find the width, which is X minus A. That's why X minus A times 1 over B minus A will be the area to the left. This means the probability, cumulative probability X less than X. Okay, so this is the some explanation of this for uniform distribution, and you can use this to calculate. You replace like A by 6, B by 10. Let me see. Oh no, 0 to 10. A is 0, B is 10, and you get B minus A equal to 10. So the height is 1/10. And now if we want to calculate area less than 3, that means the area between 3 minus 0 over 10 minus 0 is 30%. So on and so forth. Just calculate the area under the curve. Okay. So with that in mind, we better go faster. Okay, so these are the formula. We don't have time to explain. Actually, if you follow this right, is calculate, is proof is here. Proof is here. How do you derive those formulas? Okay, they can all be proven. All right, now normal distribution, this is a formula. Normal probability distribution is by far the most popular one, and it's a bell shape, look like this one. The most commonly used normal distribution is the one that has center. It means the peak, the maximum, the peak, okay, the mode occurs at mu equal to 0, and with standard deviation equal to 1, we call this standard deviation. So is a standard deviation, and so equal to 1. So we call it standard normal random variables. This is most useful. This is a special member in the normal distribution family. There are infinitely many members in the normal distribution family. As long as you change its center mu and its standard deviation, everything else will be. You will generate a new member in this family. Okay. Okay. Yeah. All right. Now let's see. Okay. You have different normal distribution families, but you can all through standardizing them to make them members in this family. So for example, this question. Let's look at this question. X follow a normal distribution with n 0, 1 and calculate the probability z greater than or equal to 1.13. Okay, so yeah, so this is normal distribution family. What's the probability that z greater than or equal to 1.13? So this is area that we as the answer to our question. Okay, because probability is area. Okay, so for how do you calculate that question? You can use a table, but I love to use a statistic again. You can use a statistic. Okay, under statistic analysis, you will see normal distribution, and you click on 1.13. Evaluate. You can see what? All this information right here. You have cumulative, you have lab area, which means to the left of this value under the curve, 0.8707. The area to the right under the curve, to the right of this value under the curve is 0.129. 0.129. You see that? 0.129. So, and you see this is much easier to refer to the table. And it also gives you the value that's what? Central, which is 0.7415. Central means what? If you draw point negative 1.13, the counterpart of 1.13, and the area to the left will be equal to the area to the right of 1.13. Then the central area will be 1 minus the 2 tails. 1 truncate the 2 tails. The remaining area will be the central area, and it's also calculated already by statistics for you. So I suggest that you use statistics as a table instead of using a paper table, and this will be easier. Now the next question will be calculate the probability x is between negative 2.5 and 10, given its center is 5 and the standard deviation is 4. How would you calculate this question? you may do a little bit standardizing. Okay, let's see. Yeah, right here. Okay, that's -5 on both sides, on all sides, -5, -5, -5. Okay, so you have, let's cover the let's ignore the denominator for one second, and so you see -5, and then this z is actually x -5. Then you divide 2 on all sides. You see this right here, because x -5/2 equals to z. Okay, so that's how you do the standardizing. So instead of you looking at x, you look at the z. But then for the z, you it's included now by 2.5 and -3.75. Okay, so so how do you calculate this area? What you can do is find the area of let me do this for you. Oh, I need to. One second. Okay. Okay. Let me draw a graph. Okay. This refers to x, but to standardizing, because 5 is in the center. Okay, or I draw it here. Here. I move the center to here, 0. And this is z. So 5 corresponds to 10 to x -0/2. So 10, sorry, -5/2. So I plug in 10 -5/2 is 2.5. Let's see. Yeah, 10.5. Okay. Right, and this number 5, plug in here also. 2 minus 5 is what? -3 divided by 2 is -1.5. So this value corresponds to this value. This value corresponds to this value. And this area corresponds to this area. So in order to find the probability, right, x between -2.5 and x by 10, you equivalently you calculate area -1.5 z. Okay, but how do you get this area? How do you get this area? That being said, you have to find the area to the left of 2.5 and subtract the area to the left of -1.5 to the left. Find this area first and then subtract this area from it later. You will have this area left, this area, which is this area as your answer. So how do we do that? I would suggest that you use either Excel or StatDisk, plug in 2.5 analysis, plug in 2.5, you'll find area to the left. You type this number in Excel, and then type in what? Negative 1.5. You write down this number. You subtract 0.066A07 from 0.993 something. You will get the answer. Okay, so this is how you use statistics to solve for all these questions. All right. Okay, we move on. So that, and I will skip this formula parts. Gamma probability more or less the same, but the gamma probability is derived from gamma function. All right. In other words, if you integrate this f of x with respect to x from 0 to infinity, you will be able to get the total area under the curve equal to 1. Okay, this is how gamma changes when its parameters changes. Okay. All right, I'll leave this to you for the sake of time now. In principle, these probability distributions are have essentially same features, which is the area under the curve are 1. Regardless what curve they are, they must be 1. And there are parameters that determines the different characteristics, the most important characteristics of the curve, of the we call it PDF in terms of continuous random variable, and PMF in terms of discrete random variables. Okay, all right. Now, for the sake of time. Okay, so this 3.2. Now we have to cover 3.3 as well, and 3.4. So a little bit challenging. We'll do our best. Now for the joint probability distribution, think of, let me move on to the continuous. Think of, instead of two-dimensional, it's a three-dimensional. It's three-dimensional now. It's no longer two-dimensional because the probability depends on two random variables, and they changes together simultaneously. So instead of looking at it as a surface, you look at the distribution as a volume. The area under the curve is 1. Hold on one second. The area under the curve is 1. Then the volume under the area in the volume will also be 1. Okay, so this is the basic difference. All right. Let me see if there is no graph here for me to show. No. there should be a well, actually this is not very accurate. It must be three-dimensional. This graph that's shown here, this graph that's shown here, you need to spend a little bit time working on this in order to get the probability area. Okay, and so covariance is a little bit challenging. You need to have the concept of space. Have the think of it as a volume, Okay. Let me see. X equal to 0. I may show you the correct graph I did for this 3.3.3 example, instead of, because if you look at this graph, it may be kind of misleading and may not get the point. I will send I will post the solution in addition to this one to you with a better graph. Okay. This is by random variable. In other words, you don't just look at the one variable. You have to look at two variables. And let me go back a little bit. And because they are joined, the probability is joined together. There's an example. Okay. Anyway, yeah, you will work on it and you will get the feeling about it. Okay. I think, what time is it? Oh, it's almost an hour. Okay, I don't have time to go over the assignments. Well, I will let you work on it, and I will see what I can do to help you in addition to that. But I think this is a good point to call it a day, call it off, because.
Okay. If I have any questions.
I don't want to overwhelm you, and it's time for you to eat dinner as well.
Yeah, I can smell it now.
I hope I can smell it too.
I'll tell her that.
That must be delicious.
I wouldn't say any other thing.
Wonderful. Okay, you are so blessed. Okay, awesome. Yeah, as mentioned, I'll conclude it this way. As I mentioned, this is quite, it's getting more challenging. Even to cover this in the lecture, it's not easy. And even the examples have some typos or even mistakes. So I will send that to you, and you do your best to work on those assignments. Okay.
Okay.
And whenever you have questions, don't hesitate. You don't have to type everything if you don't have time. Just take a picture of your written answers and then merge all of them into one Word file. If that's easier for you, I don't mind about that. Okay. Okay. I think I'll stop here. Okay. But you can always post your question in discussions in addition to the discussion question for assignment question as well.
Great. Thanks very much.
Okay. You are very welcome. Enjoy your dinner. Okay.
Thanks.
All right. Okay. Okay. Have a great weekend. Bye bye.
Goodbye. You too.
God bless. Okay.